Hello, I'm Guillermo, a researcher from UPM, and I'm going to go a bit into the detail of the design of the radio frequency generator for this project, which remember we want to integrate together with everything with the rest of the power supply. So first of all, let's have an overview of the thruster. So the thruster in this case is a gridded iron thruster, which is basically a box with the propellant inside of it. It also has a coil going around of it, and this thruster generates thrust by applying an electric field and pushing out ions. So we need two things. We need the electric field, which is generated by applying high voltage, positive and negative high voltage to the screens. These screens have a grid of holes, hence the name of the thruster. And we also need to ionize the propellant, which is typically xenon. To ionize the propellant, we apply a high frequency sinusoidal current through the coil that goes around the thruster, and this generates a magnetic field inside of the thruster that ionizes the xenon. Additionally, we also have a neutralizer which just gets rid of the electrons in order to maintain the ship neutrally charged. So the important part is that the radio frequency generator needs to generate a high frequency sinusoidal current to ionize the xenon. So in the classical approach, as Javier explained earlier, we have the radio frequency generator together with the thruster, far away from the electronics supplying the power. This is because we need to join the electronics to the thruster with a really long harness, typically, well, in this case, meters long, from 6 to 11 meters. And placing the harness before the radio frequency generator allows us to have a DC harness, which is much easier to design and has smaller losses. For this project, we wanted to put the radio frequency generator on the platform side. Why? Because the thruster gets really hot, so dissipating the heat from the radio frequency generator is hard, but also because this allows to integrate everything together, reducing the weight and the cost of everything. In exchange, we now have a harness working on AC, which is much harder to design. So the harness design is harder, but also the design of the radio frequency generator, due to the effect of the harness being at the output, is also harder. So to model the thruster, well, the radio frequency generator is a coil at the output that is generating a magnetic field. And this is the same as a transformer, where the primary of the transformer is the coil itself, and the secondary is the plasma inside the thruster. So we can put everything on the primary side, and this is the equivalent model of the thruster, an inductor in series with a resistor. So this is our system, and we need to deliver a sinusoidal current with a really high power, 1 kilowatt of power. So what we do is we place the resonant capacitor in series, and we use a regular inverter here. So the inverter creates a square voltage, and thanks to the resonant network, we have a high efficiency, high power resonant current, which is also sinusoidal, of course. Also, the thruster is not a constant load. Depending on the thruster behavior, we have a changing resistor and inductance value. And since the inductance value of the thruster changes, the switching frequency that the radio frequency generator needs to work at, it also changes. So this is also important. We need the inverter to work at regular switching frequencies. So now let's see what happens when we place the harness after the radio frequency generator. So the harness can be modeled as a network of RLC, as a distributed RLC network. But for this project, we can lump everything together into a single RLC network. This network only models the first resonance of the harness, but is enough for this project. So now this is our circuit. And what is the new problem now? Well, we have this parasitic capacitance here caused by the harness, and this gives another path for the current. So we now have a new current, and this creates an additional resonance that we do not want on the circuit. So we have the current going through the thruster is the resonance that we want, but we have extra current going through the parasitic capacitance of the harness that we do not want. So you can see here on the admittance body, without the harness in green, we have only the resonance of the thruster. After placing the harness after the radio frequency generator, we have this additional resonance caused by the harness. And this is a problem because remember we are using a square wave, square voltage to create the sinusoidal current. Of course, the square voltage has extra harmonics at high frequency, and some of those harmonics will fall close to the harness resonance and will create extra current. So this is the prototype. You can see radio frequency generator here on the right, the harness in the middle, and then the load, which is an inductor in series with a resistor. And we are measuring the current at the input of the harness and at the output of the harness. And if we do this, well, the ring current at the output of the harness, we can see is the sinusoidal current that we want. But then at the input of the harness, we have the sinusoidal current with some extra harmonics, and which is the effect of the parasitic capacitance. You can also see this effect on the FFT, where we have the harmonica switching frequency, the one that we want, and then in this case, at 7 times the switching frequency, we have an additional harmonic. Okay, and also we need to be able to follow the variation of the switching frequency caused by the variation of the load inductance. So we need to close the loop, and in this case, we are using a current transformer with a comparator to measure when the current is positive or negative. But the problem here is that we want, well, remember, we want to integrate everything together before the harness. So the current that the control sees is not the green one that we want to coordinate with, but the yellow one. And this has extra harmonics that will cause problems for the control. So we are using a digital control that limits the maximum switching frequency. But okay, for the 6 meters harness, this works well. We are able to close the loop at full power, no problem. But if we try to close the loop with the 11 meters harness, which has a bigger high frequency harmonics, we can see that the control is switching at a frequency that excites the high frequency harmonics. Even though we are limiting the maximum switching frequency, in this case we are switching at 5 times, well, at a fifth of the harness resonance, and we are exciting it with the fifth harmonic. So the effect of the harness is that we have extra current harmonic that has a extra high frequency currents. This creates extra losses and also affects the closed loop. So we need to filter the harmonics somehow. So we need to add a filter. The first idea is to add a bandpass filter. Okay, and you can see that at high frequency, yes, after adding the filter, the admittance is smaller, but the filter behaves as an inductor at frequencies bigger than the resonance of the filter. So we still have this resonance here caused by the harness. So we need to damp this resonant peak somehow, so we can add a resistor. If we add a resistor in parallel, you have here in blue the admittance of the filter alone, and you can see how the resistor of the admitter or the filter limits the peak of the resonance of the harness resonance while keeping the resonance of the thruster the same. Okay, what's the problem here? Remember, we need to work in a range of switching frequencies, and you can see how we can design the filter for the middle point, but then we will also need to be able to work at frequencies here where the filter isn't as good. The admittance of the filter here isn't as high. So what's the problem here? If we look at the filter, ideally we want all the thruster resonance current to go through the bandpass filter, and all the high frequency harmonics to go through the resistor path. The problem is that we have two parallel impedances, and part of the fundamental component will also want to go through the resistor path. How much current we want to go through the resistor? Well, it depends on how close these two impedances are to each other. So in the ideal case, like here, you can see that the impedance of the bandpass filter in green is far from the impedance of the resistor in red. And so in this case, it works really well. But imagine we have the switching frequency around this point. Now the impedance of the bandpass filter is much closer to the impedance of the resistor, and a bigger current will go through the resistor, which creates a lot of losses and makes the design not work. So in order to solve this, we need the resistor path to have a high frequency, a high impedance at a lower frequency, while keeping the resistive behavior at higher frequency. So what can we do? We can add a capacitor in series to the resistor, and you can see now that the impedance of this path is much higher at lower frequencies thanks to the capacitor, while keeping the same resistive behavior at higher frequencies. And here is a comparison of the two filters. The filters are exactly the same. We just added a capacitor here, okay? And you can see without the capacitor, we have the fundamental component here of the current going through the resistor, which creates a lot of losses. After adding the capacitor, we only have the high frequency harmonics, and the losses are much smaller. So we were able to reduce the losses from 24 watts to only 8 watts. So this is the design filter prototype, which is the bandpass filter path here and the resistor with the capacitor path here. And this is a comparison of the simulation and the prototype. You can see that in the simulation matches pretty well the prototype behavior. The only difference are these higher frequency ripple that we see on the prototype, but that's because on the simulation we are using the simplified model of the harness, okay, that only models the first harmonic of the harness. These high frequency harmonics but they're really small and are caused by the second and third resonance of the harness. So the model works pretty well. The filter works well. We were able to go from the case of the left with these really high frequency harmonics to the case on the right. And more importantly, we are now able to close the loop correctly. So before we had the high frequency harmonics affecting the closed loop. Now the control correctly switches at the frequency of the load. So in conclusion, placing the radio frequency generator before the harness creates extra harmonics on the radio frequency generator, which creates extra losses and makes us unable to close the loop. To solve this, we place a filter, and this filter has a capacitor and resistor in parallel, where the resistor dampens the amplitude of the high frequency harmonics, allowing to close the loop, while the capacitor makes the resistor losses not that big and allows us to have a really big resistor for filtering without that many losses. So that's everything from my part. Thank you very much.